The 8086 microprocessor, it was the first 16-bit microprocessor, and it is available in a 40-pin IC. Means this IC 8086 IC, it has 40 pins, and also this 8086 microprocessor, it is available in different clock rates. So we can write here the feature of the 8086 microprocessor, that it is a first 16-bit microprocessor. It is a 40-pin chip, and it is available in different clock rates. Like its clock rate can be 5 megahertz, 8 megahertz, and 10 megahertz. So depending upon the clock rate value, there are various versions of this 8086 microprocessor. Now coming to the mode of operation of the 8086 microprocessor, it operates in two modes. First is the maximum mode, and second is the minimum mode. Okay, so in minimum mode, the microprocessor, it works as a single processor, and in maximum mode it works as a multiprocessor system. Okay, so this 8086 microprocessor, it can operate in single processor configuration also, and in multiprocessor configuration also, to achieve high performance. Now as this 8086 microprocessor, it has 40 pins. So these 40 pins, some of the pins, they can operate in either maximum mode or minimum mode, or both maximum and minimum modes. Okay, so here we can write that some of the pins, they have functions which are operated in the maximum mode or in the minimum mode, or both the modes. So the same pin, it can be used in both the modes, in minimum mode also and in maximum mode also. Minimum mode is the mode in which the 8086, it operates in single processor configuration, and maximum mode is the mode in which the 8086, it operates in multiprocessor configuration. So let us now study the pin diagram of 8086 microprocessor, which consists of 40 pins. So let us first see the pin diagram. So this is the pin diagram of 8086 microprocessor. You can see that it has 40 pins. On one side it has 1 to 20, and on the other side it has 21 to 40 pins. And every pin is assigned a signal here. So let us see. On pin number 1, we have the VSS, or the ground. From pin number 2 to pin number 16, we have the address and the data bus AD0 to AD14. Then we have AD15 here, and A16, 17, 18 and 19. So the address bus, it is of 20 in the 8086 microprocessor. So we have the 20 address lines starting from AD0 to A19. Okay. Then we have NMI, okay, INTR, clock, and again VSS, ground. We have two connections for the ground. Then 21, it is reset. 22, ready, test. QS1, QS0, then S0, S1, S2, lock, RQ, GT1, RQ, GT0, then RD bar, minimum and maximum mode, bus high, enable, and S7. These are the status signal: S3, S4, S5, S6 and S7. Then we have the VCC where the plus 5-volt power supply is connected. Now here you can see that two modes are described. One is the maximum mode and other is the minimum mode. So in the maximum mode these pins work, and in minimum mode these pins 31 to 24, these pins they will have these signals, okay, which are described here, written here. Like pin number 31 in minimum mode, it will act as the hold signal. 30 pin, it will act as HLDA, hold acknowledge. Then write, this is memory and input output operation. This is data transmit and receive. Then this is data enable, this is address latch enable, and this is INTA. So these signals, they will work when the 8086 it is operating in the minimum mode. In maximum mode these pins will work as RQGT, not the signals which are written here. So you can see that there are some pins which have the functions in both the maximum mode and the minimum mode, and some pins are there which have a particular function either in the maximum mode and the minimum mode. So now let us study the description of all the pins of the 8086 microprocessor in detail. First we will start with the power supply signals. In the power supply signals, we have the ground and the plus 5-volt power supply. As the 8086, it operates at the plus 5-volt power supply. So at the pin number 40, plus 5 volts VCC is connected and ground is available at two pins, pin number 1 and pin number 20. So for power supply signal 8086, it uses So 8086, it uses plus 5 volts DC supply. At pin number 40 we have the VCC, that is plus 5 volt connection, and at pin number 1 and pin 20 they are acting as the ground. Okay. Then we have the frequency signals or the clock input. So clock signal or clock input, it is provided by pin number 19. You can see in the pin diagram that at pin number 19 we have the clock input. Now this clock input, it provides the timing signals to the processor so that it can perform various operations. So here I have written that this clock signal, it provides timing to the processor for operations. Now 8086, it has different versions like 8086, 80861, 80862, and these versions, they operate at different clock frequencies like 5 megahertz, 8 megahertz and 10 megahertz. So we can say that the operating frequency range of 8086, it is between 5 megahertz to 10 megahertz. Okay. Next we have the address and the data bus. The 8086 microprocessor, it has 16-bit data bus and 20-bit address bus. So we can say here that it has 20 lines for address, which are from A0 to A19, and it has 16 lines for data, which are from D0 to D15. Now these address and the data bus lines, they are multiplexed with each other. So 16 data lines and 16 address lines, they will be multiplexed. So when they are multiplexed, they are collectively known as the 16 address and data lines are multiplexed. So they will be together known as AD0 to AD15. So in this pin diagram, you can see that we have AD0 to A14 available from pin number 16 to pin number 2, and pin number 39 is also AD15. So we have AD0 to AD14, which are from pin number 2 to pin number 16, and AD15, it is available at pin number 39. Now, how to differentiate that on these 16 address and data lines when address is available and when data is available? So, during the clock cycles of the microprocessor, during the first clock cycle, the address is available on these address lines, and after first clock cycle, data will be available. So if we divide these 16 address and data lines into two 8-bit lines, then AD0 to AD7, it will carry the lower order data byte, and AD8 to AD15, it will carry higher order data byte. Okay. Now during first clock cycle, address is available on these lines, and after first clock cycle, data is available on these lines. So this 16-bit data, it will be available at the AD0 to AD7 and AD8 to AD15, and the 20-bit address, it will be obtained by combining the 16-bit data lines AD0 to AD15, and then A16, A17, A18 and A19. Okay, so in this way we can get the complete 20-bit address and the 16-bit data. Next, we have the address and the status signals. You can see in the pin diagram that the address and the data bus, they were multiplexed from AD0 to AD15, and the remaining address lines, they can work as these pins 38 to 35, they can work as the 4 address lines also, and as the 4 status signals also. That is from S3, S4, S5 and S6. So here we will discuss the address and the status signals. So this is like A16 to A19, or it can either work as S3 to S6. Okay. So these lines or these pins, they can act both as the address bus also and as the status bus also. So how it will be differentiated, that at what time address is available and at what time these pins are acting as the status signals. So during the first clock cycle, the address will be available, and after the first clock cycle, the status signals will be available. Okay, so during the first clock cycle, we can get the complete 20-bit address by the address lines AD0 to AD15 and A16 to A19. And after the first clock cycle, the data in the address bus, they will represent the data, and the A16 to A19 lines, these pins will carry the status signals. Okay. Next we have S7 or bus high enable. This signal, it is available at pin number 34. You can see that we have two signals, means it can act as bus high enable also, and it can act as the status signal S7 also. Okay, so let's see that what is the function of this signal. This BHE, it stands for bus high enable, and it is available at pin number 34. So this signal bus high enable, it is used to indicate the transfer of data using the data bus D18 to D15. So the higher order data byte that will be transferred by using this signal bus high enable. Now this signal, it is low during the first clock signal. So you can see here that it is an active low signal. So it will be active during the first clock cycle, and when it is active, it means that the data available on the bus, it is the higher order data, and that has to be transferred. Okay, so this indicates the transfer of data using the data bus, and this signal is low during the first clock cycle. Next we have the read signal. This read signal, it is available at pin number 32. We have RD bar, and its full form is read. So it is available at pin number 32, and this signal, it is used to indicate the read operations, means whenever the microprocessor, it is performing the read operation, then this signal is low because it is having a bar over it, so it's an active low signal. And this signal is used to perform the read operations. Okay, so it means that whenever this signal is active, it means that the microprocessor, it is performing the read operation. Then we have ready. This ready signal, it is available at pin number 22. You can see at the pin number 22 we have this ready signal. Now this signal is used by the microprocessors or by the peripheral devices. Peripheral devices means the input output devices which are connected with the 8086 microprocessor. Now it happens that whenever the peripheral devices, they want to communicate with the processor, so the 8086, it is having a very high processing speed, but there are some peripherals which do not have such high speed. So if they want to cope up with the speed of the 8086 microprocessor, then they send this ready signal. The microprocessor wait for some time till the input output devices or the peripheral devices, they come to with it, or they match up with its speed. So at that time, the microprocessor will wait for some time, and when the input output devices, they are ready for communication with the microprocessor, then they send this ready signal. So this ready signal, it is used by the peripheral devices to indicate the microprocessor that it is ready for the transfer of data or we can say that it is ready for communication with it. Okay. So this ready signal, it is available at pin number 22. So this ready signal, it is an active high signal, and we can also say that it is an acknowledgement signal from the input output devices that data it is ready for to be transferred, means the device is ready for communication with the microprocessor. And when this signal is high, it indicates that device is ready for transferring the data, and when this signal is low, it indicates wait state. Wait state means that when the signal is low, it means that the input output devices, they are not ready for communication. So the microprocessor, it has to wait for some time so that the input output devices, they match up with its speed, or they first finishes their current operation, and then they will perform the transfer of data with the microprocessor. So when this signal is low, it indicates wait state for the microprocessor. So this is the ready signal. So next we have the INTR signal. This INTR signal, it is available at pin number 18. You can see in the pin diagram at pin number 18 we have INTR. The full form of this signal, it is interrupt request. It means that when this signal is given to the microprocessor 8086, it means that some peripheral or some input output device, they want to interrupt the microprocessor. Means they are sending a request to interrupt the microprocessor, so that microprocessor first finishes its operation and then it executes the service routine of that interrupt. Okay. So we have the signal INTR. This is interrupt request signal. This signal is available at pin number 18. So this is an interrupt request signal INTR. Now every time the microprocessor, suppose it is executing an instruction, so this instruction, they will be executed in the form of clock cycles. So at the end of the last clock cycle of each instructions, means when the instruction is executed and the microprocessor reaches to the last clock cycle of that instruction, then at that last clock cycle, this instruction, this pin INTR will be checked. If this signal is active, means this is given to the microprocessor, then it means that microprocessor is interrupted, and then microprocessor has to finish the execution of that instruction and then jump to the location or at which the service routine of that interrupt is written. Okay. So this signal, it is checked during the last clock cycle of each instruction, and when this signal is given, it means that the microprocessor is interrupted at that point. Okay. Next we have NMI, which is the non-maskable interrupt. NMI is available at pin number 17, and the full form of this is non-maskable interrupt. This signal means that the interrupt is given to the microprocessor, and the microprocessor cannot mask or it cannot deny this interrupt. It has to, in every situation, it has to execute that interrupt. Okay. So next we have NMI, non-maskable interrupt. It is available at pin number 17. So this is a type of interrupt which cannot be masked by the microprocessor, and it is an edge triggered input which interrupts the microprocessor. Okay, and it is available at pin number 17. Next we have the test signal. This test signal, it is available at pin number 23. Here we have at pin number 23 the test signal. This is an active low signal. So this signal is available at pin number 23, and this signal is like the wait state. So when this signal, it is because it's an active low signal. So when the signal is low, then the microprocessor, it continue its execution of the instructions, means it will perform and it is going to operate in its normal functions. Okay, normal mode. Now when this signal is high, then the processor, it has to wait for the idle state. Okay, so when this signal is low, the execution continues in its normal way. But when the signal is high, then the processor has to wait for the idle state. So we can say that this signal, it is used when the microprocessor, it is communicating with the peripheral devices where it has to wait for some time. Okay. So this signal is just like a wait state for the microprocessor. Then we have MN or MX bar. This signal, it is available at pin number 33. You can see here we have MN and MX bar. So when this signal decides that whether the 8086, it is operating in the maximum mode or in the minimum mode. So when the signal, it is low, it means that it is operating in the maximum mode, and when the signal is high, then the 8086, it is operating in the minimum mode. Minimum mode means that the processor, it is in the single processor configuration, and maximum mode, that means the processor, it is operating in the multi-processor configuration, means there are several processors which are connected with each other. So it is available at pin number 33. This is for minimum and maximum mode. So this is the minimum maximum mode signal, which indicates that in which mode the processor, it is operating. Okay, so when this is high, it means minimum mode is there, and when it is low, it means maximum mode is there. Then we have INTA, which is the interrupt acknowledge signal. whenever the microprocessor it is interrupted by the peripheral or some input output devices, so in response to the interrupt request given by the peripheral devices to the processor generates an output signal which is known as the interrupt acknowledgement signal. This signal means that the microprocessor has received the request of the peripheral devices that they want to interrupt the microprocessor, and now the microprocessor has received that request. Okay, so it is kind of an acknowledgement signal. So this signal it is available at pin number 24, and the microprocessor send this signal whenever it acknowledges an interrupt. Next we have the ALE signal. The full form of this signal is address latch enable. So by the name of this signal, you can get an idea that this signal it is used to enable the latch on the address bus. Okay, so the address will be available for a longer period of time, and also it is used to demultiplex the address and the data buses. This ALE signal it is available at pin number 25. So this signal it is available at pin number 25, and when a positive pulse means when the signal is high, then every time the processor begins any operation. So every time the microprocessor it is starting any operation like read, write. So anytime when any operation is started, this signal is high. Okay, and when the signal is high, it indicates that a valid address is available on the address and the data bus, because we have the address and the data bus as multiplexed with each other, that is AD0 to AD15. So to distinguish that on these bus whether data is available or address is available, this signal is used. So when this signal is high, it means that address is available on these buses. Okay, so every time the microprocessor it is starting any operation like read operation, write operation, it needs the address of the memory location. So before starting any operation, a positive pulse means this signal is active, high, this signal will be generated. Okay, next we have DEN, that is data enable. You can see that this DEN it is available at pin number 26. Okay, so this pin these signals they are active in the minimum mode. Okay, these ALE, INTA which we have studied, they are also applicable only in the minimum mode of operation. So this is the data enable which is at pin number 26. Now this data enable signal it is used to enable the trans receiver IC 8286. So this trans receiver it is a device which can transmit the data, means it can transfer the data also, and it can receive the data also. So whenever we want to enable the data or whenever we want to transfer or receive the data from the 8086 microprocessor, then this data enable signal is used, because this signal it is going to enable the 8286 trans receiver, which is acting between the 8086 processor and the input output devices. Also, the AD0 to AD15 address and the data bus, it is carrying both the address and the data. So if we want to separate the data from this bus, then also this trans receiver is used. So whenever we want the data to be available, then we use this signal to enable the trans receiver IC 8286. Next we have DT or R. The full form of this is data transmit or receive. So this signal it is used to indicate the direction of flow of data. Means whether the data it is coming towards the 8086 or it is going out of 8086. So it is to indicate that the data transfer it is either the flow of data it is either towards or it is either outward from the 8086. So this is for data transmit or receive. This is available at pin number 27. So this signal it is used to decide the direction of flow through the trans receiver, whether the data is transmitted or whether it is received. So when this signal is high, it means data is transmitted, and when this signal is low, it means the data is received. Because on the received we have a bar, so it means that this will be active when its value is low, and this will be active when its value is high. Okay. The next signal we have is MIO. So this signal it is for the memory and the input output operations. Means this signal will indicate that the operation performed by the 8086 it is either a memory operation or an input output operation, like whether it is memory read, memory write, or input output read and input output write. So this signal it is for memory and the input output operations. It is available at pin number 28. So this signal it is used to distinguish between the memory and the input output operations. When this signal is high, it means that it is an input output operation, and when it is low, it means that it's a memory operation, and it is available at pin number 28. Next we have the signal WR. This is for the write signal. Just like we have the read signal, we have the write signal also, which indicates that the operation performed by the microprocessor, it's a write operation, like memory write or input output write. So this WR, it is available at pin number 29. So this write signal, it is used to write the data into the memory or the output device, depending upon that which operation is selected. Okay, and this signal it is an active low signal. So when it is 0, its value is 0, then only the write operation will be performed. Next we have HLDA and hold. HLDA, it stands for the hold acknowledgement signal. This acknowledgement signal, it is used when the microprocessor it is performing the communication with the DMA controller, and this it is an acknowledgement signal for the hold signal given by the other processors. So we can say that it is hold acknowledgement, or this signal indicates that it 8086 it has received the hold signal. Okay, so it is just a response towards that. It is available at pin number 30, and this signal indicates the acknowledges the hold signal. Now next we have the hold signal. Now this hold signal indicates that there are some of the processors which want to communicate with the microprocessor, and they want that the microprocessor relieve the control of its buses to those processors, so that the processors they can have control over the buses of 8086. So hold, it is a request which is given to the 8086 that the other processors they want the control of its buses like address bus, data bus, and the control bus. It is available at pin number 31. Okay, so we can say that these two signals are for the hold signals like DMA execution. DMA, it is the direct memory access controller. We will study these two signals in detail when we study the interfacing of DMA with the 8086 microprocessor. Next we have the QS1 and QS0 signal, which are the Q status signals. Now we know that this 8086 microprocessor, it has a special feature of instruction queue. Means that whenever it executes any instruction, then it has the quality of prefetching 6 instructions at a time. Means that the operation code of 6 instructions can be fetched at same time. Okay, so these 6 instructions they will form a queue. So what is the status of the queue? That is revealed by the two signals QS1 and QS0. These two signals they have different combinations, and those combination they will indicate different status of the queue. These are available at pin number 24 and 25. So we have the conditions for these two signals QS0 and QS1. First we can have 0 0, then 0 1, 1 0, and 1 1. So when these two signals are 0 0, then no operation is there, no operation will be performed. When it is 0 1, then first byte So in the queue, we have the opcodes for the instructions. They will be stored. So when this QS0 and QS1, they are 0, 1, then the first byte of the opcode will be fetched from the queue. Then if we have 1, 0, then this is going to empty the queue. And if it is 1 1 means subsequent byte from the queue. Subsequent byte means first byte is already being fetched, so the byte which is next to this byte, that will be fetched from the queue. So depending upon the status of these two signals, the following operations will be performed. Next we have S0, S1 and S2. These three are the status signals, and these status signals, they decide the type of operation performed by the 8086, like whether it is memory read, memory write, input output read, input output write, or it's the opcode fetch cycle. So all these operations, they are decided by the three signals S0, S1 and S2. These are the status signals. So these signals, they provide the status of the operation. And they are available at pin number 26, 27 and 28. You can see in the block diagram, we have 26, 27, 28, the three status signals S0, S1 and S2. So let us see the combination of these three signals, that what the three combinations, they describe the kind of operation. We have S2, S1 and S0. We can have different combinations like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Then we have 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So three signals, they can have the 8 combinations. So when it is 0, 0, 0, it means interrupt acknowledgement. Means the processor, it is going to acknowledge the interrupt and it is going to generate the INTA signal. Okay. Then we have 001, so that will be an input output read. Means the operation performed by the microprocessor will be an input output read. It is going to read the data from an input output device. Then 010, it is input output write. 011, it will be the halt state. 100, it is opcode fetch. 101, memory read. 110, memory write. And 111, it is passive. So these 8 combinations, they decide that which is the status or which is the type of operation performed by the microprocessor. Next we have the signals lock, you can see that in the block diagram we have at pin number in this pin diagram we have the pin number 29 as the lock signal. So this lock signal, it indicates that the microprocessor, it has locked its buses, means like the other input output and the peripheral devices, they cannot have a control over its buses. Okay, so this signal, it indicates that the other processor, they should not ask the microprocessor for the control of its buses. It is available at pin number 29. So this lock signal, it indicates other processors not to ask the CPU to leave the system bus. Now how this signal is activated? This signal can be activated by writing the prefix lock at in front of every instruction. So we can write the lock prefix on any instruction. So the next signals we have are the RQ, GT1 and RQ, GT0. These are the request and the grant signals. So we can have the request and grant first, then we have request and the grant 0 signals. So we can write here we have the request and grant signals. So whenever the microprocessor means whenever other processors or the peripheral devices they want to communicate, they are sending some requests to the microprocessor that they want the control of its buses. Now in response to that request, the microprocessor it generates the grant signals that it has granted the request, it has accepted the request and it has granted that the other processors or the peripheral devices they can have a control over its system buses. Okay, so whenever the peripheral devices they are communicating, they send these request signals, and in respect to these request signals, microprocessor issues the grant signals. So when the processors they are going to request the CPU to release the control of the system bus, and when this request is received by the CPU, it sends the acknowledgement, means it is going to send the grant signal. Okay, now suppose that two input output devices they want to communicate at the same time, so two requests will be generated. So how to decide the priority? The priority is decided that RQ and GT0 it has the highest priority or higher priority than RQ and GT1. So first the system buses will be given to the processor which is connected at this GT0 and then at GT1. Okay. So in the pin diagram we have seen that we have studied all the pins. We have first we studied the power signals like VSS and the VCC. Then we studied the address and the data bus. Then the address and status signals. Then we studied the ready, rest, reset, test, QS0, QS1, and the status signals also there. Then NMI, INTR, non-maskable interrupt, interrupt request, clock signals. Then we have the pin number 31 and two pin number 24. These pins they have dual functions, means they can work as in the minimum mode also their function is different, and in maximum mode their function is different. Now if we want to relate it with the signal diagram of 8086, then we can see that this is the signal diagram, and if we relate it with the pin diagram, we have the power signals VCC ground here connected. Okay, then we have the clock input here. Then we have interrupt interface signals, means signals which are related with the interrupt operation of 8086. So for interrupt we have the INTR, then INTA signal, non-maskable interrupt, and the test signal. Then reset signal, it is used to clear the contents of or to restart the execution of 8086. Okay. Then we have hold and HLDA, which are used when for the DMA interface. Whenever the 8086 it is interfacing with the DMA controller, direct memory access controller, then these two signals are used. Then we have the mode select signal, which is the minimum and the maximum mode selection. Then we have memory input output controls, like we have memory input output signal, which decides that whether the operation it's a memory operation or an input output operation. Then we have read write, data enable, ready signal, data transfer, transmit and receive signal. This is bus high enable or the status signal 7. Then address latch enable. So whenever any memory or input output operations are performed, then these signals are used. Then we have the multiplexed address and the data bus AD0 to AD15, and then we have the A16 to A19 address bus, which is also used as the status signals S3 to S6. So all the pins on this pin diagram, they are categorized into various signals in this signal diagram. So the description of the pins and the signal, it remains the same, only just you have to categorize the pins in various signals. Okay. So in this video, we studied about the pin diagram and the signal diagram of the 8086 microprocessor. So I hope that this topic is clear to you. Thank you.